Alright, in this video we'll be going through the 2016 electricity exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you completed the question or get stuck, unpause the video to see how I go about getting the answer. Eleanor sets up a circuit to investigate how capacitors operate. The circuit is shown below. The circuit includes a 2.2 times 10 to the negative 6 farad capacitor and a double pole switch. Calculate the maximum charge stored on the capacitor in the circuit. Alright, so when maximum charge is stored on the capacitor, this is when the voltage across the capacitor is equal to the voltage across our power supply. And so in this case, that is 5 volts. And so therefore, Q is equal to CV, and we are given our capacitance of 2.2 times 10 to the negative 6, okay? And that's multiplied by 5 volts, and that equals 1.1 times 10 to the negative 5 coulombs. The capacitor is initially uncharged, and the switch is in the position shown. Eleanor moves the switch to S1, and the capacitor charges up. The graph of the capacitor voltage against time is shown below. Use the graph to calculate the resistance of the resistor. Draw lines on the graph to help explain your working. Alright, so the switch is moved to position S1, so it's moved to this position right here. Okay, so as you can see, this circuit is an RC circuit. Alright, because we have our resistor here and our capacitor here. And what we want to do is find the resistance of the circuit, so this resistor value right here. And so the way we do that is by using our time constant, where our time constant is equal to the resistance times the capacitance. And so therefore our resistance is equal to the time constant all over our capacitance. Now remember, after one time constant, our voltage is going to rise to 63% of its max value. So 63% of 5 volts, okay? And so 5 times 0.63 is equal to 3.15 volts. And so 3.15 is going to be roughly right over here on the graph, okay? And so as you can see, that is roughly at 1.1 seconds. And so our time constant is going to be equal to 1.1 all over our capacitance, which is 2.2 times 10 to the negative 6. And this gives a resistor value of 500,000 ohms. There we go. Give a comprehensive explanation for the shape of the capacitor voltage graph. Include reasons for the starting and final voltage. Okay, so we know that Q is equal to CV, and so therefore the voltage across the capacitor is equal to the charge across the capacitor divided by the capacitance of that capacitor. And so when the switch is first closed, the capacitor is going to be uncharged, meaning that there is no charge on the capacitor plates. And so when there's no charge on the capacitor plates, obviously our Q is going to be equal to 0. And so therefore our voltage across our capacitor is going to be equal to 0 also. But also when the switch is initially closed, that is when charge is going to begin to flow. And so therefore the charge is going to flow onto the capacitor. And at this point, this is when the charge is going to be moving its fastest. And so therefore the current is at a max. As more charge begins to accumulate on our capacitor plate, the charge that is already on the capacitor plate is going to repel any oncoming charge, because like charges repel. And so therefore the current will start to slow down, and so charge will accumulate on the capacitor plates at a slower rate. And so therefore the voltage is going to start to rise even slower. And so what we had initially is a huge voltage rise. As this process of repelling charge takes place, the rise in the voltage is going to slowly drop off. When the capacitor is fully charged, this is when the voltage across the capacitor is going to be equal or almost equal to the voltage across our power supply, okay? And so therefore we're going to have two opposing EMFs which are equal to each other, and so therefore the current is going to be 0. And so therefore no more charge is going to accumulate onto the capacitor plate, so the voltage is at a maximum value and will no longer change, and so that's why we get the tapering off on our graph, okay? And I can move this over here so you can see that shape better, like so. There we go. Eleanor connects another 2.2 times 10 to the 6 farad capacitor in series with the original capacitor, and repeats the experiment. Describe and explain how this affects the final voltage across the original capacitor and the time constant of the circuit. Okay, so because we have our power supply here, and that was 5 volts, okay? Now we have two capacitors in series like so. So because these two capacitors are identical, the voltage across them is going to be the exact same, because they have the exact same properties. Okay, and so now because there's two of them, the voltage across them is going to be half of what it would be if there was just one of them, which when there was one of them, it was just 5 volts. And so it's going to be half of that, so it's 2.5 volts each. Okay, so the final voltage across the original capacitor, let's say this was the original capacitor, is going to be half of that what it was before. Okay, so we ticked off this point. And the time constant of the circuit. For the time constant of the circuit, we obviously know that that is equal to the resistance times the capacitance. And so in order to calculate the capacitance when we add capacitors in series, we use this equation right here, okay? if you want to know where this equation came from. It was one of my first videos that I made, and I also went through it again in the electricity video. It's one of the capacitance videos, can't remember which one. But if you watch the videos, you probably checked it out. But anyways, as we can see here, if we plug in our numbers, okay, we have 1 all over 2.2 times 10 to the negative 6 plus 1 all over 2.2 times 10 to the negative 6. Okay, the total capacitance will decrease. It will decrease to 1.1 times 10 to the negative 6 farads. Okay, so as you can see, our capacitance has decreased, and so therefore our time constant must decrease. Okay, and so we ticked off that point. Transformers can be used to increase or decrease the size of an AC voltage. Wei, is that his name? Wei has a transformer that is designed to convert 240 volts into 12 volts. The secondary coil has 40 turns. Calculate the number of turns in the primary coil. Alright, so this is a pretty simple question to start us off. We know that NP all over NS is equal to VP all over VS, where P stands for primary and S stands for secondary. Okay, we're trying to find the number of turns in the primary coil, and so therefore we can rearrange for NP like so, okay? And so now we can just simply plug in our numbers. The voltage in our primary coil is 240 volts, divided by the voltage in our secondary, which is 12 volts, times the number of turns in our secondary coil, which is 40 turns. And so this gives the number of turns in the primary as 800 turns. Here we go. Explain how an alternating voltage across the primary coil creates an alternating current in the bulb connected to the secondary coil. So the alternating voltage in the primary coil causes an alternating current within the primary coil, and this causes an alternating magnetic flux within the iron core. Remember that our coils are within this iron core thing. Okay, let's say this is our iron core, and the coils are wrapped around this iron core. I draw a better picture in my video on transformers, so if you want to see a better picture, you can go through that video. But essentially, that causes an alternating magnetic flux within this iron core, and then therefore that alternating magnetic flux within the iron core induces a voltage in the secondary coil, which results in a current flowing through the lamp, thus the lamp glows, due to P is equal to I squared R. Well, here's a better image of what the iron core looks like. I think it looks pretty similar, if you ask me. Each coil of a transformer acts as an inductor. The primary coil is attached to a battery and a switch as shown in the diagram below. The switch is closed and then sometime later the switch is opened. Sketch a graph showing how the current in the coil changes when the switch is closed and then sometime later is opened. Give a comprehensive explanation for the shape of your graph. Alright, so the shape that we're going to draw is something that looks like this. Straight down. So the reason for this, when the switch is initially closed, there is therefore going to be a current flowing through the circuit. And so therefore our current is coming from zero. And so there's going to be a high rate of change of current. And so because we know the back EMF equation for our inductor is equal to negative L, change in current all over change in time. If there's a high rate of change of current, therefore we're going to have a high back EMF, okay? And so due to this, we're going to obviously, like I just said, have a high back EMF. And so this back EMF is going to oppose the oncoming current. And so therefore, instead of the current reaching a max value straight away, we instead see the current rise slowly, okay? However, over time, there is going to be no rate of change of current, okay? And so therefore, this back EMF is going to die down. And so therefore, there is no longer anything impeding the current from flowing. And as we can see, the current reaches its max value. However, when the switch is opened, there is a open circuit, and so therefore current can't flow anywhere, and so current must drop to zero instantly, and that is what we see over here. And you can write that in words. Calculate the energy stored in the primary coil's magnetic field when the switch has been closed for several seconds. The battery's voltage is 6 volts, the resistance in the primary coil is 35 ohms, and the inductance of the primary coil is 0.1 henries. Alright, we know the energy stored in an inductor is equal to half Li squared. Okay, we are given our inductance of the inductor, so that's our L value. However, we're not given our current value, but what we are given is the voltage and the resistance. And as we know, due to Ohm's law, that is all we need to know to find the current. And so we get 6 all over 35, okay? And I'm going to keep it like this in order to keep whole values. And so we get half L, which is 0.10, times 6 all over 35 squared. And this gives an energy of 1.47 times 10 to the negative 3 joules. Vivian wants to measure the amount of iron in iron sand mixtures collected from different beaches. The diagram below shows a circuit that she uses. The circuit includes a 500 turn coil with a resistance of 15 ohms and an AC supplied. The coil behaves like a resistor and an inductor in series. The coil has a hollow core that is initially empty. Vivian adjusts the power supply voltage to 6 volts RMS. Calculate the instantaneous maximum peak voltage across the power supply. Alright, so we know that our VRMS is equal to our V peak all over square root 2. Okay, if you don't know where this equation comes from, I go through it in my electricity playlist. It's in one of the videos. It's Y is VRMS equal to root 2. Okay, so you can go check that out. But because we want to calculate V peak, we can rearrange for V peak, and we get V peak is equal to VRMS multiplied by square root 2. We know our RMS value is 6 volts, and so 6 multiplied by square root 2 is equal to 8.49 volts. There we go. During testing, Vivian puts a mixture of iron and sand inside the core of the coil. State what effect this has on the size of the coil's reactance. With reference to impedance, explain what happens to the size of the current in the circuit as she adds the mixture of iron and sand. Okay, so putting iron into the coil will increase the inductor's inductance, okay? And so because we know that the reactance of the inductor is equal to the frequency of the AC power supply, or the angular frequency, I should say, of the AC power supply, multiplied by its inductance, if the inductance increases, therefore the reactance will increase. And so therefore, because our impedance is equal to square root XL squared plus R squared, if our reactance of our inductor increases, therefore the impedance of the circuit is going to increase. And so therefore, because V is equal to IZ, if our total impedance has increased and our voltage remains the same, therefore our current must decrease within the circuit. And so therefore you can write that in words. When Vivian sets the frequency of the current to 1000 Hz, the inductance of the coil is 3.18 times 10 to the negative 3 henries. Using a phasor diagram or otherwise, calculate the size of the RMS current in the circuit. Alright, so if we go up here, we can see that our resistor has a resistance of 15 ohms, okay? And so as we should know, we can redraw our voltage phasor diagram in terms of our resistance, impedance, and reactances, okay? And that's because when we have a series circuit, the current is the same at all points throughout the circuit, and so therefore, if we just remove the current, instead of showing a diagram of voltage, we instead show the diagram of the impedances, okay? And so therefore, we can draw a phasor for the resistance value, and that's 15 ohms, okay? So that's our resistance value. We can calculate our impedance value, okay, and that's equal to 2 pi f times L, okay? Remember that this is equal to omega, okay? It says that our frequency is 1000 Hertz, and so therefore we can plug in our numbers, and it also says we have an inductance of 3.18 times 10 to the negative 3, okay? And so this gives a reactance of 19.98 ohms. And so therefore, our reactance vector is going to look like this. This is 19.98 ohms, and this is the reactance of our inductor. And so therefore, our total impedance is going to be this phasor right here, okay? And so if we do vector addition, we can find this phasor, where we have our resistance value coming to the right like this, our reactance coming up like this, and so this resultant vector is going to be our total impedance, okay? So this is 15, this is 19.98, and so therefore, our total impedance is equal to square root 19.98 squared plus 15 squared. And so this gives a total impedance of 24.98 ohms. Alright? And so therefore, VRMS is going to equal to IRMS multiplied by our total impedance. Our VRMS is given in a previous part right over here as 6 volts. And so therefore, IRMS is equal to VRMS all over our total impedance. And so therefore, 6 all over 24.98 is equal to 0.24 amps. There we go. Vivian adds a capacitor in series with the coil and finds that the current increases. Explain why the current increases. Okay, so this is because in our vector diagram, okay, if we draw a vector diagram, the reactance of our capacitor is 180 degrees out of phase with the reactance of our inductor, okay? And so therefore, they are going to cancel each other out, or at least partially cancel each other out, okay? We know that when they totally cancel each other out, that's when the circuit is at resonance. However, we can't quite say that in this case because we're not given the information that the circuit is or is not at resonance, okay? So we're going to say that the reactance of the inductor and the reactance of the capacitor partially cancel each other out. And so therefore, as our total impedance is equal to square root XL minus XC squared plus R squared, if due to us adding a capacitor has now made this value smaller, okay, because again, due to the fact that they are partially canceling each other out, but our resistance obviously remains constant because that's just a resistor. Therefore, our total impedance is going to decrease. Okay, and so therefore, due to V is equal to IZ, if our total impedance has decreased, therefore our current must increase as our voltage has remained constant. Okay, and so you can write that in words. And with that, we are done.